Hello everyone, my name is Tarindu. I'm from University of Monato and I'm going to talk about the work I did this summer with Google Summer of Chord. We look at chord features of input chord and track how the chord features change over time when LLVM applies optimizations. And I'll also show you how we can use these chord feature changes to optimize our chord much more efficiently. Developers usually have to use predefined set of optimization pipelines to optimize their code. So optimization pipelines are a set of predefined passes which are applied to LLVM IR in order to optimize the code. So LLVM has standard optimization levels like O1, O2 and O3, and developers manually have to select which level they need for their code. The problem with this is these optimization pipelines are not tailored for any kind of application, but rather they are designed to work for any kind of generic application. These are the chord features we look at. We look at things like the basic block counts, numbers of different kinds of instructions like load and store, and loop depths. And there are many more chord features we can look at in the literature, but these are the chord features we could look at during the summer. Here is one chord feature, the basic block count, change over time for one module from CTMark benchmark, and when we apply O3 optimization to it. And each of these lines represent a function from the module, and there are gaps in the middle for each line. That's because like different functions get different passes applied to them, so some of the passes are not applied to some of the functions, so that's why there are gaps. And the x-axis is what we call the hyperpass pipeline, so we had to align these passes using sequence alignment algorithms. So this is what we came up at the end after aligning all the functions. Here's how the rest of the chord features and how they change over time. And something interesting here is you can notice some of the passes does not like change any of the chord features we are looking at right now. So that's something interesting. Next, we wanted to see if we can cluster these functions into groups using the features we extracted. So we came up with 7 clusters. So each color in this graph represents a cluster of functions, and in the second graph we are making it like a bit more easier to visualize it. We are representing each cluster using just one function, the function with the maximum number of passes. And the motivation behind clustering is if we can predict a cluster early on in the pass pipeline, we can tell LLVM that we do not need to apply some of these passes to this function because it doesn't change that. So we actually came up with a predictive model that could predict the cluster each function belonged to with an 85% accuracy after looking at the chord features after only 30 passes. So there are around 300 passes. So now we do not need to apply all 300. We can, after the 30th pass, we can tell LLVM this function belongs to this cluster, and that function does not need some of these passes you are applying. So we can significantly save compile time and resources. As a start of how to use these clusters, we look at LLVM standard optimization levels. So we took a set of functions and we compiled them using O1, O2 and O3 optimization separately, and compared the assembly files and categorize them according to the level of optimization they need. So in this figure, the red each point represents a function, and the red ones only need O2, and the green ones only need O3, and the blue ones only need O1. And when we look at the clusters 3, 4 and 6, we can safely say they only need O2 optimization, and clusters 1, 2 and 5 require a little bit more work. What we can do is we can maybe introduce more clusters, or maybe we can introduce more features, and that's it. So if you have any questions or if you want to help me with your resources, time or ideas, please feel free to contact me, and thank you.